Saptarshi, we can start if you're okay
Yeah,
with.
yeah. Of course.
So good evening, everyone. Today we have the last talk for category C of the day by Saptarshi Halder. He pursued his bachelor's from Ramakrishna Mission Vidya Mandira, Belur Math, and then went on to pursue his master's from ISI Bangalore. And now he is pursuing his PhD from University of Texas, Dallas. He will be talking on introduction to complex geometry. And over to you, Saptarshi.
Yeah.
Thanks.
Thank you everyone for joining, and I hope this camp is enjoyable so far. And also, I thank to the organizers for giving me the opportunity to speak here, and it means a lot to me. So let us start. Okay. Okay. So I will be talking about today's introduction to complex geometry. So basically, my current topic of research is this complex geometry, or more specifically Halder geometry. But I want to give a introduction to the complex geometry because I will try to focus on some elementary parts, not going to deep theory because it will take a long, because the theory is so developed and uh, so equipped that we have to have a very good amount of time to prepare all those theory. For today, I will just give the intuition and some basic things. Uh, Please let me know if you cannot see the screen or if you didn't understand anything. Just let me know. Okay, I will be happy to stop and understand, explain to you. Okay, okay. Let us start. So, first of all, what we need to know is that why complex geometry? We have this geometry, right? The real differential geometry, but why the complex geometry? So in real differential geometry, what we have is the curves and the surfaces like these things, uh, and more generally the manifolds. Okay, real differentiable manifolds. Okay. Now, so what we will do after defining a manifold? After defining a manifold, it's a natural interest to define a function. Okay, and some special kind of function, maybe continuous functions, or maybe more regular functions like C infinity functions. Okay, on that. There, if we can define a C infinity function over a particular neighborhood, now using partition of unity rho, we can define it globally because this partition of unity we can consider, which is a C infinity. You can take it as a bump function for now, maybe like this, what I have given here. Just multiply it with that function and it will give you a global function which is C infinity. Okay. And now, but the thing is, this partition of unity, construction of this partition of unity is not general or not very intuitive in complex manifold. So I will later explain what is a complex manifold. But as of now, those functions, just not only C infinity, we have to have some holomorphic conditions. Okay, like it must be analytic, but we are not sure that a function, does there any functions so that we can do these things, like it vanishes identically outside the neighborhood and it's holomorphic too and it's C infinity, but we don't know we can do this or not. It fails actually. So that's why um, the study of this complex geometry begins, and we can say this the structure is more rigid than the complex real thing. Okay, so what we have, that complex differentiable holomorphic functions are more rigid, and in a domain which is open and connected, um, a holomorphic function f is completely determined how it behaves inside a small neighborhood around a single point. Okay, not globally, and we want to extend it globally, but we don't know is there any way to do it or so. Okay, like in smooth functions, real manifolds, we have if we have a function, then we just multiply it with the C infinity bound functions or the partition of unity, we can extend it globally. But here we don't. In that sense, the complex manifold makes this notion more rigid. Plus, so underlying manifold is a complex manifold. So I will explain what's complex. Okay. Before going to that, we will be talking about Cn when n is greater than or equal to 1, and the holomorph. What is called the, or what is called the meaning of this holomorphicity in Cn? So if we have a open subset of Cn, and we denote this local coordinates z1 up to zn, and this zz splits into xz plus iyz, where xz and yz are in R, then we say a function f from that domain, open subset, to C is holomorphic at a particular point. Remember this thing, at a particular point z, if f is continuous at z and it's complex differentiable with respect to each zj independently. Means for with respect to each z1, z2 and up to zn, as we are in Cn, it should be complex differentiable. Okay, so what should be the equivalent definition of this function if we consider it like a real thing? So basically this complex thing will boil down into real dimension 2n, because it's Cn, so real dimension is 2n, and we consider a function from a subset of this u of R2n to R2. Okay, and what we have that, because here we broke down is zz into two parts, xj and yj. Here also this xj and yj will be there, and what additional f will satisfy? Additionally, f will satisfy the Cauchy-Riemann equation. Okay, as we see in elementary complex analysis. Okay, okay. So what does this Cauchy-Riemann equation mean? That so first define this del del z is equals to this half del xj minus del of del yj, and this del del z j bar, because we have two things here, zz and zz bar, this expression. Now the shear equation will tell you that the function should be del del of del z j j bar is equal to 0. Okay, for all j equal to 1. Okay, so this is the thing what we want to focus on. This is what we say holomorphicity means. Now I want to tell you that, so we know many popular formulas or things or the theorems in complex one dimension, but the thing is they are not true in general or in complex 2, complex 3 these dimensions. Okay, they are not true. Sometimes they fail to be true. So we have some different notions for higher complex dimensions. Okay, okay. So let me tell you one theorem that is called Hartogs extension theorem. For observe that for n greater than 1, strictly greater than 1. Okay, not just n equal to 1. We will soon see that why I told those things just before. Okay, so for n greater than 1, maybe C2, Cn, C3, C4, Cn. So this little bit different. So what is this higher Hartogs extension theorem says? So if you have n greater than equal to 2 and this sigma and this open subset of Cn, and k is also a subset of omega, and it's a compact subset. Okay, it's a compact subset. Okay, such that if we consider such that this thing omega result k is connected. Okay, if it is connected, you can assume it's path connected because the norm or the topology is the Euclidean topology. Just just that is the thing. It's connected means nothing beyond, but just the path connectivity. Okay. Now, what this theorem says is that every holomorphic function. So, if you define a holomorphic function over here, this part to C, it can be extended. This can be extended uniquely. Not only extended, it can be extended uniquely to a holomorphic function if tilde from whole domain, the whole domain is omega over here, to C. That is the statement for n greater than 1. Okay. Now I want to show you how it differs from our natural intuition for C. Okay. Just complex analysis, just one dimensional complex analysis. Okay. Now, if you take this omega to be C, just the complex numbers, and if you result this 0, singleton 0, we are taking, so basically what we are doing is that we are taking k to be 0. It's a singleton set, it's closed. Okay, it's closed, and moreover it's compact. Moreover it's compact. Now observe that this thing C result 0 is connected, because if we consider it like this thing, if you don't have this point, so any 2 points anywhere, any 2 points can be joined using path. You can avoid easily this point. So it's path connected. So it's connected. But if we define fz equal to 1 over z, observe that it is defined in whole C result singleton 0, but it is not defined at 0, and it cannot extend. Okay. 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 So this is one example where we can see that in more dimension, means n greater than 1, things may behave differently. Okay. Any questions so far? Okay. Okay. Let me proceed to the definition of a complex manifold. So a complex manifold X of complex dimension n, remember this thing, complex dimension n means it should be a subset of Cn. Okay, it should be a subset of Cn. Should be a subset of Cn. Okay, it's Hausdorff. I think you know Hausdorff. What is this mean? Just in basic topology sense. And second countable. Okay, and that what we have this the coordinate chart as we define in the real differentiable manifolds. We also define here the coordinate charts like this if we have these 3 conditions. So first one is u alpha is an open cover of X. Okay, and we have phi alpha, which is from u to v alpha. V alpha is open, is a subset of Cn, is a homeomorphism. And these transition functions, these are called transition functions from a different chart to another chart. So basically this psi alpha beta of phi alpha compose phi beta inverse, this thing, because just observe, actually they agrees on this intersection part. Okay, these, when we study the real differentiable manifold, they were just smooth functions. Okay? But here we have additional criteria, which is holomorphic. Okay, which is all holomorphic, and its inverse is also holomorphic. Okay, C infinity. Okay, but we need extra condition that it's holomorphic, and this inverse is also holomorphic. Okay, so that's what um, complex manifold means, so if we, for any subset of Cn, if we can do these things, we can define these things separately, we can tell that that is a manifold of dimension n. Okay, complex manifold of dimension. Okay, so it's natural thing that what are the examples? Okay, now one example is very easy, means is trivial. Is you just take Cn, the whole Cn. It's a n-dimensional complex manifold, because you just take the identity functions to be these functions, and the open set is Cn itself. So one single means thing. Yeah, you can write it as just uh, the Cn and the identity. That's it. Okay, that will make you the give you an example of complex manifold of dimension n. But we need to focus on something different. We just see some abstract example. So what we have over here is that this gamma, it's a lattice. So a lattice means a point. So a point in R2, like if we have this uh, coordinates from Z, these are all belongs to Z. Okay, integer coordinates you can take. Okay, so it's a lattice. Now if this Cn, if it is quotiented out by this Zn, so basically what we are doing is that in topological sense, if you have a grid like this, if you have a grid like this, so these are all these lattice points here, and you are identifying all of this to be one. Okay, so it will give you torus. Okay, so and topologically it's S1 cross S1 up to S1, 2n copies. Okay, so basically for one, if we can, if you take it as one, then if you just have one identification, so suppose you have like this grid and just you identify these 2 points, if you join these 2 points and these 2 points also join, then you will get like this, huh? And this is precisely S1 cross S1. Okay, this is the thing. So this is a complex manifold, but we yet not defined what are the um, charts or this atlas thing we have over here. We can define it, but I have not defined it here. Okay, but it's a complex manifold. Okay, you can define, you can check that. Now one of the most interesting thing is that complex projective space. Okay, so what is going on over here in the complex projective space? So what we consider is that the complex projective space is Cn plus 1. You just resolve this 0, so Cn plus 1 without 0, and you will you quotient with the equivalence relation. Okay, so the equivalence relation is this. Okay, so that means basically if you have one something a point over here, so if you have a total sphere and if you have this point, then this equivalence relation over here will give you the whole line. Okay, the whole line. So you are identifying this whole line to be one limit. Okay, so you get all possible this identification will give you this space. It's hard to visualize, but this is one of the easiest way to do it. Okay, to identify the lines. Okay, okay, so so here I can give you the explicit, I am this open sets. The open sets are like this when Zg is not equal to 0. Okay, these are the open sets. So this is a subset of Cn plus 1. Observe that, remember that. So it should contain n plus 1 coordinates. Okay, it should contain n plus 1 coordinates. Now the functions phi j are like z0 to zn, and so on uj the zg is not equal to 0. Okay, so we can divide by zg because it's not equal to 0. The domain is like that. Okay, we can define it. So what this hat means, that means this coordinate is not there. So this is the function. What makes this whole CPN is a manifold, complex manifold. Okay. Okay. So we have seen one trivial example and two non-trivial example. And remember that this CPN is very interesting thing. Actually, it contains a lot of information. Okay. So these are explicitly studied in this area of research. Now we move on to some thing that we need to know. Okay, so the thing is, so we are in CN. We have this maximum modulus principle like C. Okay, we have this. So now if X is compact, connected, complex manifold, compact and connected at the usual sense, nothing different. Compact means closed and bounded, and connected means the path, simply path connected. Okay, nothing different. Okay, so a complex manifold. Now if you have a global holomorphic function f such that f from X to C, then it must be constant. Okay, like what we have seen in Liouville's theorem in just complex analysis. Okay. It holds here as well. Okay. Next, okay. Next, we talk about little bit advanced things. So first of all, X is an n-dimensional complex manifold, complex dimension n, and we denote XR is the underlying smooth real manifold. Okay, with real dimension 2n. Okay, because this complex dimension in real dimension should be 2n. You can treat it as means you know from the vector space things. Right? So it's a real manifold with real dimension 2n. Okay. Now, if we take a point P at X, we can talk about its tangent space, right? You know the tangent space, right? So if you have, suppose if you have a curve, if you have a point over here, you can draw a tangent. And now if you have a surface, then you can talk about its tangent space, right? So these are, so let me denote it. This is a tangent space. Okay. Okay. This is the tangent space. So we consider the tangent space at that point P of XR. Okay. Okay. So observe that this TPXR, it each element gives a endomorphism, naturally a endomorphism. How? Because this X is a complex manifold. So if we take a element from here, suppose let's say capital X, and if you send it to IX, iota time X, then it remains on this tangent space. So it's an endomorphism. You can natural endomorphism you can do. Okay. So now we'll be talking about these things. So now what we define is a complex structure. Okay. So we need to give some complex structure to do some so-called analysis or the calculus on this manifold. What we wanted to do, what we were doing very easily on the real manifolds, real differentiable manifolds, but we want to do it over complex manifolds as well. So I will tell you the steps, how should we proceed. Okay. Okay. First of all, we need to have a structure, okay, on a manifold M. So the structure is called the almost complex structure. So that is on a smooth real manifold. We are giving an almost complex structure on a smooth real manifold because we know how it behaves, how TPXR behaves, because it's a real dimensional manifold. XR is a real 2n dimensional manifold, and this TPXR is the tangent space at that point. Okay, we know how it behaves, we know the theory over here, but we don't know about the complex thing of X. Okay, we want to know that. So in that aim, what we want to impose a complex structure, okay, on the real, some smooth real manifold, say aim. Okay, here it is XR. Okay, we call this J a smooth tensor field, and J belongs to these things. This, if you know, otherwise it's okay that it's a we call it, this is a special space of global sections, because we consider this Tm to be a vector bundle over M. Is a Tm is the total space, and this means the sections. So sections is basically kind of the going inward in opposite direction from A to Tm. Okay, so this global sections can be means written as a, like, you can write it as like, suppose uh, suppose if you have xj del del j, these things, it can be a global section. Okay, it can, so we define it like this, capital. Okay, okay. So now this j, for this j, we call it almost complex structure if we have this thing. So z square means is z compose z is equals to minus identity. Okay, this is the endomorphisms, and we are observing the section, global sections of this endomorphism. Okay, okay. Any questions so far? Okay, if not, let me proceed further. So what we have is that a almost complex structure z, and so we tell this to be almost complex structure if this thing and this thing holds, means z square equal to minus identity. Okay, now if we have X, we consider it as a real manifold, maybe 2n dimensional, we can naturally define, these things, this thing. So you know this j is acting on these elements. Okay, 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 this is the section, so it should eat an element from Tm. Okay, so this is del del x j, j of del, we define, naturally we can define del del x of j is equals to del del of yj. Okay, these are the partial derivatives. Okay, and j of del del yj to be negative del del xj. Okay, over here. Now observe one thing. Now if we compose j with j, you will get minus identity, because if we compose over here, then a z will come over here and it will be minus del del yj. It's just minus identity. So naturally, so this any real manifold x, can naturally have a almost complex structure. Okay, this is the precise thing where you can see that it naturally contains or naturally admit a almost complex structure. Okay, now we want to know more about this almost complex structure J. So we define Tc of x like T x of R tensor with C. Okay, so this is called the complexification of this tangent space. Okay, so what we have, z square is equals to minus identity over tcx. You can check that this map can be easily defined like this tensor thing. Okay, so now it is a map, right? It's a global section, so z belongs to j belongs to this thing, endomorphism of Tn. So we want to know about its eigenvalues. Okay, we can tell something about eigenvalues. So if we consider complexified version of this tangent space, means this TCX, this, the eigenvalues I and minus I will make sense. because in real there is nothing I and minus I, right? There is nothing like that thing. But if we complexify it, if we complexify that um, tangent space with C, tensor it with C, you make it complexified, like we denote it like TCX, then we can talk about its eigenvalues, and the eigenvalues are precisely I and minus I. Okay, because Z square equal to minus identity. Okay. So from this thing, I and minus I, so now we can talk about the eigenvectors, and you know that these things. So TCX, TRX, all are vector spaces, right? You know that these are all are the vector spaces. Okay, it also have the same dimension as the manifold. Okay, so these are the vector spaces. So what we can do, as we know that different eigenvalues will create different give different eigenvectors, and those eigenvectors will generate a vector subspace. Okay, and the whole vector subspace, here it is TCX, can be written as the direct sum decomposition of those eigenspaces. Okay, this is just the elementary theory of vector space, like V is equals to Vi direction V2. Okay, so from this TCX we got these two things corresponding to I and corresponding to minus I. Now, we need to define what are these. So T10 of X is all those Y belongs to TCX, such that JY is equals to IY, because I was the eigen value over here, and you can write it like span of del Z ZJ. This is in local coordinate. This is in local coordinate. Okay, because we have seen that this TCX, the elements are precisely looking like this over here. Like you can tell it like it's a vector field. Okay, this vector field. So the vector fields will look like precisely this summation x del g bar del g. So we can define this T10X to be this thing. Okay, and for T01X we can define it like this, because minus iota was eigenvalue over here. So this space can be written as is y TCX and jy going to minus iy, this the span of this thing. We need to consider this z j bar thing. Okay, okay, the conjugate one. So these are two splitting the part where this TCX can be written as like this thing, this and vector space direct sum of this thing, these two things. Okay, so what is the need of these things? I will tell you why this almost complex structure is not sufficient to do analysis or the calculus on that complex manifold consistently. Okay, so to introduce the notion of calculus on X, what we need something more. Okay, that means J, we call it J needs to be integrable. So what does it mean by integrable? Okay, this integrable means J should originate from a global consistent local set of holomorphic coordinates. Okay, why this is true? Because in what we have that a function in the complex from Cn, its holomorphicity, everything, it's based on a point and a small neighborhood around that. But if we want to do calculus or the analysis on the whole manifold, that small information is not good or not going to help us to do that. We need a global information. So for this thing can be defined it globally or not on the whole manifold, it depends on this J is integrable or not. Okay, so if that those things can be defined very consistently on the whole manifold, then we call G's to be integrable, and G integrable means that. Okay, this is basically the definition. So this is the main step where we need J to be integrable to do all these analysis things or any further theory on the complex manifold. Any questions? Okay. Okay. So, um, so what do you mean by the calculus? So there are two coordinates over here. One is two things going on over here. One is with respect to zg and what is zg bar, what we have seen earlier. So these and there's a conjugate one. Now, so one can easily ask, or one can directly ask that when the complex manifold must have a integrable structure. Okay. So there is a criteria. This is this criteria. This is called Nijenha's tensor. So J should be integrable if and only if this thing is identically zero. What is this means? These are just the Lie brackets. Okay. So x and y are vector fields, and Jx again a vector field because J was from the endomorphism of Tm. So it's again a vector field. We can talk about this tensor quantity, and this is called Nijen-Hughes tensor. Okay, but this is not the point. The point is that if this thing, whole thing, is identically zero, okay, then we call this J is integrable. So to check a complex manifold have a integrable structure or not, we can check that the Nijen-Hughes tensor vanishes identically or not. Okay, this is the same thing we can. Okay, it's just a criteria. Okay, it's just a criteria to check these things. So it's a popular theorem that's, I think it's Newlander Nirenberg, due to Newlander and Nirenberg. Okay. So so we have seen that when this J integrable almost complex structure J is integrable when this Nijen-Hughes tensor is identically zero and vice versa. Okay. Now we have the tangent space, so we can talk about the tangent bundle. The tangent bundle is basically the Tm from, okay. So maybe I can write it like, so Tm this on M, this just the tangent bundle. You can talk it like that. So now for this tangent bundle, you can have a splitting of complex differential forms. Okay, so I will tell you what this complex differential forms means. So so this is what we denote. This omega k c of x is the smooth complex valued k forms. Okay, and what we have that this omega kx tensor with r to c. This is on r. This thing is on r, and we have this thing. It is also a direct sum decomposition. Okay, direct sum decomposition of this thing. So we call alpha. Now we can give the definition of this complex differential forms is like alpha is, so you can think it as a dual space. Okay, like if you have TPM, you can have T star PM, right? If TPM is a vector space, you can always talk about its dual space. Okay, it's T star PM, right? Or for TM, it will be T star. Okay, so basically these elements are from there. Okay, so from there, so what we can define is for alpha in omega pqx, we it's smooth complex valued k form, so it can be expressed locally as like this. These are like functions. Okay, these are smooth functions. Okay, so we have observed that we have this is a natural way to write a forms alpha from here, and this is so this is up to I1 up to IP and J1 to ZQ. Okay, because it's from here. It has two components, means P numbers of this I just Z components and Z Q numbers of Z bar components. Okay, Now we know what is D's standard exterior derivative as like real differential and differentiable manifolds. So D will take a function of a form K form to a K plus 1 form. We know that. Okay, D will take this D map will take a K form to a K plus 1 form. Okay, what we have seen in the real differentiable manifolds. Now here what we have is that D can be splitted into two parts, this del part and this del bar part. So this del bar part corresponding to the del of zj bar, and this del part is corresponding with del j g zj. Okay, these two parts. Okay, so now so you can see that from this del thing operator, it sends this omega pq to omega p plus 1 q, and this because it acts only on the first part, this part. Okay, it will only act on this part, and this del bar part will send this and a form this thing to omega p comma q plus 1, because it just acts on this part. Okay, so it will rise a degree of this part. Okay, similarly over here, so these things. Now if J is a complex structure, so what we have is that this d square equal to 0. Okay. D is the exterior derivative, so d square is anyway equal to 0. So that will imply some things, because this d is equals to del plus del bar, we can calculate d square, right? Decompose d. So we will have these three things. Okay, you will have these three things. So del bar plus del bar del equal to 0, and del bar square is equal to 0, and del square equal to 0. Okay, so now observe that this del bar square, so del square actually it's not a problem. The problem is what restricts to do all these things natural is that conjugate part, that z bar part. So this del bar, we focus on this del bar square is equals to 0 part. So observe that this del bar square equal to 0, this give you some notions. What are these? So as del bar square is equals to 0, we can construct a chain complex like as we in Dirham complex, like this from 0 if you have, sorry, over here. Okay, so from 0 we just do the del bar thing, and it will give you this this. Okay, let me, yeah. So you will get this omega pqx, and if we take an element from here, and if you do the del bar, if you just use the del bar operator, it will rise a degree over here, so omega p1x. And similarly for these things, and if omega pnx, now if you use del bar over here, so it's the top degree form, so there is nothing after this. Okay, we know this. If we implement this del bar operator or this d operator on a top degree form, it will vanish, it will give you 0, right? So this is the whole chain what we have. So we can construct the cohomology group. Okay, we call it Dolbeul cohomology. So this is the cohomology group. So what it calculates, so basically not each element from here it's del bar exact, right? Not you can take any element, and if you do del bar, that will be equal to 0. It's not like that. Okay, it's not exact. So it measures what this cohomology group measures. It measures this, it's how far is from the exactness. The sequence how far is from the exactness. So this is exact sequence. We want this to be an exact sequence, but we measure by this Dolbeul cohomology that how far it is from there. Okay, so we define this HPQ del bar of x it to be the kernel of del bar. So you can see that there are, I mean, so over here, if you take it over here, this thing and this thing, you can talk about the kernel del bar of this thing and the image of this thing quotient. Okay, so this is the Dolbeul cohomology group to measure how far this chain is behind from exactness, del bar exactness. Okay, so this thing now so these are some thing that we can do without any metric, so-called metric. So what is the metric? Just in Euclidean space, you just take the Euclidean distance. This defines your metric. Like, is metric nothing but you can tell about talk about, like, if you have a vector space, you can give it a inner product, like. So these are metrical like that thing, but we will tell you what is going on over here. But what we have done so far, it's not doesn't care about any metric whatever we have. Okay, now so what we can always talk is a metric we call G, popular. So G on the underlying real manifold XR, and we called this XRG is a Riemannian manifold when this G is a Riemannian metric. So we call this Riemannian manifold. Now we call this G a metric is Hermitian if this condition hold. Now we are stepping it up. So here we have this almost complex structure J, and it's an endomorphism. So Jx is belongs to Tm, and Jy is also belongs to Tm. So we if this criteria, if this thing satisfies, we tell that G is a Hermitian. Okay. So basically, so G is from Txr to Txr to R. Okay. So this is because these are the vector spaces, right? These Txrs are vector spaces. So these are vector spaces. So we can tell it this G to be an inner product, like this. I have written over here. So here, what we give, what this G to be Hermitian means, this G gives takes two elements from Tx, this Jx and Jy, and spit out this G of x comma y. These both the thing are same. Then it's called Hermitian. Okay. Now, given a Hermitian metric G, so basically then Hermitian metric. So what it has first of all this, it should be a Riemannian metric over this xi, and it must be Hermitian over here with respect to this almost complex structure J. So we can talk about 1-1 forms, right? Like suppose in DG wedge, so DG wedge DG bar in C1. Okay, you can talk about it. So we can talk about this 1-1 form in Cn. So on that complex manifold X maybe, so it will satisfy this criteria. Okay, so this omega of xy, we call it 1-1 fundamental 1-1 form if this thing holds. It's a metric, right? So so this form x and y will take two entries as those vector fields and will spit out real number or complex number, because we are in a complex setup, complex manifold. So G will take the Jx and y, and we define it like that. Now, one of the most interesting thing is that we in this thing after defining this thing, we can tell it something more. We can tell something more, that if G is a Kähler metric, we call G to be a Kähler metric. It's a special name, Kähler metric, if this d omega is equals to 0. Okay, d omega is equals to 0. So it's a huge topic of interest on X, the n-dimensional complex manifold, the Kähler structure exists or not. So basically, this Kähler structure depends on multiple things. This almost complex structure J, the Hermitian metric G, but we don't know how they exist or not. whether they exist or not, and if exist, how they behave. We don't know that. So on a random manifold, on a random complex manifold, it's not sure that the scalar structure exists or not. Okay, is it clear? Any question? Okay, so basically we are not sure like that, but we can give some example. Again, this CPN comes. This CPN admits a scalar structure. Okay, it admits a scalar structure. So under this G, we need to define this G, right? This Hermitian G, and that is for this CPN. A natural thing is to define it with Fubini-Study metric. G is Fubini-Study. So how we define this omega 1 form? We define it by this. The scalar form is omega Fubini-Study I. Some people write it like I over 2 pi, this thing, and del bar log this thing. Okay, if you do this split out this thing, you will get this kind of thing over here. Okay. So it's indeed a 1 form, and where all the thing what I have said is satisfied. So the under this Fubini-Study metric, the CPN admits a scalar structure, and the scalar form precisely this thing. But if we take S1 cross S3, the scalar structure doesn't exist at all. But there are also some manifold we cannot decide the scalar structure exists or not. Okay, so in some scenario, I'll just tell you briefly with a note that there are some manifolds. If we apply certain criteria, if you can see the result, then we can readily tell you that it doesn't admit a scalar structure. But sometimes those tests are inconclusive. Okay, I think you have studied, all of you studied this sequence of series of real numbers, right? So there are some tests regarding the convergence. Sometimes if you have a series, you can just test it and you can readily tell it it's a convergent or it's divergent. Or sometimes you have faced the situation where the test is inconclusive. So there are criteria where you can readily tell that it doesn't admit a scalar structure, but sometimes those tests fail or maybe inconclusive. Okay. So the thing is called the Hodge decomposition theorem. So it's more technical, so I am not going to that thing in this talk. So that is this has the further criterion for by which one can verify X may admit a scalar structure or not. So to admit a scalar structure, the Betti numbers, these topological things, the Betti numbers, this is the dimension of those Hodge decomposition vector spaces. Okay, this thing, and those should be even. So, but for S1 cross S3, it doesn't. So it fails to be fails to admit a scalar structure. But S6 we don't know. S6 is we don't know. We didn't able to find any scalar structure. So we first need to find out it admits a scalar structure or not. Then our next task is to give a precise scalar form like this. Okay. But for S6 we don't know yet. Okay. So, but for S1 cross S3, in that sense, in S6, those tests are inconclusive, means I don't know. S1 cross S3, we can do the computation. This is very easy computation. This is just the dimension. You just need to find out some dimension of a vector space like that. And if you have some formula, you just plug in those dimension over there and just check it even or like that. So for S1 cross S3 done. So what we have seen that so that G is a metric, but for the complex and the scalar, all the stuff, we have to be G to be a Hermitian metric. Now, so in that scenario, we can talk about connection with respect to G, because till now what we have, we had only the Euclidean sense. Okay, but with respect to this metric G, new metric, it may not necessarily a Euclidean metric, right? It can be very different, like this thing. It can be very different thing. So with respect to this, we can talk about its connection. Connections are nothing but the I will say the directional derivatives. Okay, directional derivatives. But remember this under this metric G. And after that, we can define all the curvature tensor, scalar curvature, mean curvature, Ricci curvature, all these things. So this is a whole Riemannian geometry part. Okay. So underlying a complex manifold, with the main task of those defining these holomorphic global sections and those transition functions. After doing that, with that thing, we have a real differentiable manifold, and it's a Riemannian manifold with this G metric G. So we can talk about the Riemannian geometry, whole Riemannian geometry part underlying it. So after that, it's a long theory, because we will punch uh, partial differential equations, because so these del bar of these things, we want to know this is, so we have for the scalar metric d omega must be equal to 0. So if we have, so any omega, if you need to recover that it exists or not, or if it is exists, then what is actually the omega form, we need to solve some partial differential equation. Because of this thing, we just put d over here, and this makes to be this d over here, and this is equal to 0. After that, we need to solve a partial differential equation. The solution exists or not, like that we can check that the Kähler structure, Kähler metric exists or not. Okay, so there is a long theory. So it basically turns into multiple concepts. That's the Riemannian geometry, the algebraic geometry. There are 2 points of view of doing these complex geometries in Riemannian geometry setup. So there, the PDE, the partial differential equation, it comes more frequently, and it's an extensive tool to study these two things. And but there are some notions, there are some research also in the direction of the algebraic geometry. So in the algebraic geometry, we will more interested in the shapes, categories, and those things. So there are 2 ways of study these things. So but the at the essentially, it turns out the topology. Okay, so that in both the cases we are studying the topology, but in a different way. Okay. So some of the interesting topic of this after this scalar manifold is, one of them is the Calabi-Yau manifolds. Okay, so Calabi-Yau manifold is the Kähler manifold, where this curvature we talked about this curvature, right? The Ricci curvature. This Ricci curvature is curvature. This is Ricci flat. Okay, so and there are some other manifolds called manifold. There are classes of manifolds. So all have the common questions that a complex manifold admits a Calabi-Yau structure or not. Okay, so we need to first give a existence, and then we need to give a um, um, exact definition what a form will look like. But it's a current topic. All these 3 has very emerging topic of research now, that is there exist a structure like that on a manifold, and if so, then what is the metric? Okay, can we give a metric on it, like so that this thing, all the things are satisfied, like the curvature Ricci flat for the Calabi-Yau manifold, this Ricci flat, and and the Hermitian structure, everything. So and some people ask about what is the practical implementation of the complex geometry. So the some of the application, as far as I know, is that on string theory. In string theory, complex geometry extensively used, but I don't know anything about these applications. Means how they, means how we apply this complex geometry on this string theory. I don't know. So, but I heard or I learned that this has a extensive application in string theory. Okay, let me. Thank you for your attention. I hope you enjoyed. So, before taking the questions, let me write down some references. Okay, so for further study, or you can study from directly from here, that a book. So the some textbook, the Introduction to Complex Geometry, is by Daniel, I think, Hybrids. Hybrids. This is a wonderful book, and you can search some lecture notes. Lecture notes. There are two lecture notes. One is by Andrei Moroianu, new, and one is Werner Ballman. So these are the references. So you can look onto these references if you have time. These are very good, but I will say this hybrid is more algebraic rather than this Moriano and Ballman. So if you your point of view, or you want to study through a differential geometers, I will prefer these two books, or in general for a fundamental or the first study with Daniel Hybrids is an extraordinary text. So but make sure before going to these books you have a good background in Riemannian geometry. At least one course on Riemannian geometry will help, and you can find multiple resources regarding Riemannian geometry online. Okay, so let me stop here. Thank you for the attention, and again thank you for to the organizers for giving me this opportunity to speak here. Okay, let me take some. Okay. Is there any questions?
Uh, Saptarshi, if if there are no questions, then we can thank our speaker for the talk. Thank you,
Yeah,
Saptarshi, for the talk.
yeah, yeah. Thank you. Bye.
Okay, then we can conclude the meeting here.
Yeah.
Thank you again.